earlier we learned about how when a light beam moves from a more dense medium to a less dense medium, such as going from water into air, we find that the refracted beam bends away from the normal. Now, an interesting effect occurs when the light tries to move from that more dense medium to a lesser dense medium, and we reach a certain aspect where the light becomes totally 100% internally reflected. Let me show you an animation of this. So here we have a beam of light that's going from the more dense medium. We have an optical density of 1.6, and then over here we have air, essentially, or vacuum, 1. Now, as I change the angle of incidence is here, and then there's my angle of refraction. And you can see that the ray is deviating away from the normal here. And so as I increase the angle of incidence, you can see this refracted beam is getting larger and larger. And as I increase, I reach a kind of a tipping point, and right about there, suddenly that ray is going to go right along the edge. And just as soon as you reach that special angle, then something called total internal reflection occurs. It means that anything larger than this angle right at here, like what was that critical angle? Right around there is the critical angle, 38.7. Anything larger than that angle at 45, 50, 60, all that beam gets totally reflected. None of it escapes into this other medium. And hence, that's what we call why it's called total internal reflection, because 100% of that energy is reflected internally. All right, so that special angle where you get that reflection just starting to occur right in kind of in between here, this is called the critical angle. Let's return to our notes now. Okay, back to our notes here now. So we want to show how we get this formula here. See, we're looking for the situation where the incident beam right here, this one right here, is such that the refracted beam is going to come right at that 90-degree angle. So actually, this is when you're starting to get total internal reflection. So that's that special angle where the refracted beam is really kind of skimming along the surface, that limiting angle here. Now, to get this formula, we're really just using Snell's law. We have in the incident right here, we have N1 times sine theta 1. So this theta 1 is really this critical angle. Actually, in a minute, we'll write that down. N2 is the air or whatever, the lesser dense medium. So that will be N2, and then sine of theta 2. Now, if you look here, we'll see that theta 1 we define as the critical angle, and theta 2 is the angle in the air medium, the lesser dense medium, and that's going to be that limiting case where it starts to be now right along the surface, 90 degrees. So if we substitute in 90 degrees for sine here, we're going to get sine of 90, which is just 1. And so in rearranging, by the way, this should be a C in here, we're going to get the theta, the critical angle here, is the arc sine of N2 over N1. And by the way, N2 will always, always, always be smaller than N1. You're never ever going to get total internal reflection if you go from less dense to more dense. Why? Well, it's because if you were going to go from air into water, it's always going to bend towards the normal, and the refracted angle will always be smaller than the incident angle, and there's no way you're ever going to get a refracted angle that is bigger than the incident angle. So total internal reflection only occurs when you go from more dense to less dense medium, and and that condition occurs when you are at an angle that is greater than the critical angle. Now, critical angle is going to be different for a variety of substances, and if you think of, like, for example, air is 1.0003, so we'll call that, for example, N2, and then if you do, like, say, diamond, it's about actually, it's quite high. It's 2.42. And so now, if you do the critical angle for that, you're going to find that angle is quite small. That angle in a diamond is 24 degrees, roughly. So it means that when light comes into a diamond, it starts to, really, the only way it's going to escape is if the angle that it strikes the surface at is less than 24 degrees. If it hits at an angle that is greater than 24 degrees, it's just going to reflect internally. And so Because of that fact, because diamonds have such a high index of refraction, the light that comes in, that entering light, much of it tends to just bounce around to internally reflect inside the diamond, which makes it obviously more shiny. So this is why diamonds are so shiny. Also, like periscopes, you can make periscopes with mirrors, but that's not going to be good. Remember, mirrors only, when you have that reflection that occurs, only a certain small percentage of the light gets reflected. A lot of it gets lost. Maybe you're not going to get 100% of that light. Maybe 90% of it will get through. So with prisms, you'll get 100% total internal reflection. So all of that light is going to be reflected at each of these barriers here between the glass and the air. And so that's why periscopes and binoculars tend to use prisms, because you'll get much more of that light. You'll get 100% of that light that is being internally reflected. And then the last one I'll show you guys in class, optical fibers. You see that more and more now with telecommunications. The light ray that comes in is going to be bouncing in. It's not really curving, is it? It's actually internally reflecting through this core. And these are all things that I'll kind of go over in class as well with demonstrations. Okay, go ahead and tackle some of the problems now.